I actually stopped the recording for a moment there. I think Brett just summed it up really well. What did you say, Brett? Right. Add the equations together and find the change in enthalpy. All right. Yay! And we all clapped. Okay. So here's the basic concept. The basic concept, ladies and gents, the basic concept is that we've got a reaction that we usually write down that looks like it's one step. Okay, this is a very generic reaction, but it says that A is a gas plus 2 of B as a gas winds up yielding 2 AB2s, and that the enthalpy change during this reaction is 120 kilojoules. Okay, now usually we write down reactions as one step. All right, it turns out that reactions aren't that simple. Ha, 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 ha. It turns out that there are usually steps in a reaction to get this total sum to happen. Okay, and here's the concept. The concept is that really A and B first form AB before they form AB2. Okay, and taking A and B and adding them together to form AB has a delta H of 188 kilojoules. So it's absorbing 180 kilojoules. Okay.
Yeah, you can't.
Oh no, oh my God, no.
Oh.
It's so much work.
You need to like move him up. I'm really disturbed with this position.
In step 2 of the reaction. In step 2 of the reaction, this AB that was made combines with B to form the AB2. In doing so, it actually uses 60 kilojoules of energy.
Where do you get the 120?
Okay, so where are we getting the 120 from in the total reaction?
180 plus negative 60 equals 120.
Okay, so when we add things up, the stuff on the left side, we get A. Notice, guys, on the left side, there are 2 B's on the left side. So we put a coefficient 2B.
Okay.
Notice we don't write this plus AB that's here. Because this plus AB, this AB that's on the reactant side, is canceled out by the AB that's on the product side, since there's exactly 1 on both sides.
What is this madness?
We're adding these reactions together. Okay, so this is one of the rules. If it exists on the reactant side and on the product side in the same amount and the same state of matter, they cancel out. Okay, so notice that on the product side, the only thing I've got left over to add up would be AB2 as a gas. Okay, as far as the energy is concerned, I think Emily said it, oh my God, what is this madness, the best. 180 plus negative 60 gives us the 120. So the place that we got this original reaction from was by adding up the 2 actual steps that actually happen in reality. These two reactions that are listed on the bottom, step 1 and step 2, are called intermediates. You will always be given the intermediates. All you need to do is add up the intermediates appropriately. Okay, and that's the puzzle part. All right, here's the deal. If I add up all the products and rewrite this, I'm going to get A as a gas plus B as a gas. I'm going to go to the others. I'm going to go to the reactants of step B. Sorry, I said products in the first place. I'm going to do the reactants all together. So I'm going to add B as a gas. Notice I'm getting that from here. Plus, I'm going to add AB as a gas. Now I can go to the product side. Oh, okay. So on the product side, I've got AB and AB2. So I'm going to write AB as a gas plus AB2 as a gas. Okay. So what's happening is, as I'm looking at this equation, there's way too much stuff here, right? Like, for instance, I can't move it up, unfortunately. B and B can get added together, right? Because it's the same thing. So I can say A as a gas plus two B's as a gas. When I look at this AB as a gas, though, doesn't it exist over here? If I was doing algebra and I wanted to combine my terms, what would I do? I'd subtract AB from one side and subtract it on the other side, right? So if I subtract AB from the right side and subtract it from the left side, what happens to them? They cancel out, and they're gone. Okay, so then I can write my product arrow. I can write my AB2 as a gas, and notice that this reduced summary is the reaction that's here, which is the reaction that's here. Okay, so basically what we're trying to do is we're trying to add up the steps. Okay, with that. It's pointing out on the next slide that AB is called an intermediate. It's an intermediate substance that happens as AB2 is being made. This is what makes it difficult, all right? Rule number one, if the coefficients of a step reaction are multiplied through by a factor, the delta H gets multiplied by that factor also. Don't write that down. That's complex, yes? Here's basically what I'm trying to say with that rule, okay? If I wanted to rewrite this as 2 H2O solid yields 2 H2O liquid, notice what happens to my delta H.
You got it times it by 2.
All right, does this make sense to you?
Can you put that in simpler words?
All right, so in simpler terms, if I multiply all the coefficients by a number, I need to multiply the delta H by the same number.
Oh,
Okay, so in the example here, I multiplied all of the coefficients that were in the previous problem by 2, right? So I got 2 H2O solids yields 2 H2O liquids with an enthalpy of 2 times 6, which is 12 kilojoules. Okay, had I changed it to this, oops, where's my mouse? Here it is. Had I changed it to 3 H2Os, I'd have to change the other one to 3 H2Os, right? What would I have to change delta H to?
9.03.
3 times 6 is
Oh, 18.
18. 18.03 kilojoules. Okay. Does that make sense to you guys?
Yeah.
That's balancing equations.
Yeah, that's
Yeah.
right.
Okay. So the other rule is that if a step reaction, if one of my steps is reversed, if I need to flip it around so the products are the reactants and the reactants are the products, the delta H has to get reversed also.
Like a negative?
Right. So instead of being positive, it would be negative. So for instance, if I flipped around this H2O reaction at the very top, which I modified, so if I leave that reaction at the top as it is, I could flip it so that it starts out as a liquid and ends up as a solid. That's flipped, right? I basically took the reactants and I wrote them as products, and I took the products and I wrote them as reactants.
Yeah.
The liquids over on the left side, the solids over on the right side instead.
Why did you do that? Like you wanted
Because sometimes it's helpful to flip the reaction around
so you can like cross things out?
so you can cross things out properly. Okay.
So like if we're gonna do
The ultimate here is that all that I really have to do is change it from being a positive enthalpy to a negative enthalpy. Okay, those are the only two rules that exist for this puzzle.
yeah.
And the big rule, you guys are freaking out about nothing here.
So
All
you
right.
can flip a step and
Right
just
now.
like only
You
that
you
step.
can flip one step and only that step, and you need to change the enthalpy.
Yeah.
You could also then multiply the coefficients by any number you want, but you have to multiply the enthalpy by that coefficient.
Yeah.
Okay, so rule 1 and rule 2, you can do rule 1, you can do rule 2, you can do both, you can do neither. It all depends on what the puzzle says you need to do. Okay. And the only thing that you cannot do is you cannot mess with what the overall reaction needs to look like. You leave the overall reaction alone, and you change the steps. Okay. So we want to make this overall. Should I give you guys a chance to write this down first?
Yes.
All right. Let me try and talk about this out loud. It looks to me, as I'm looking at this problem, I would leave the first one alone at first because I've got HF on the right side and I need to have HF on the right side. Okay. On the other hand, the second reaction that they give me says that water's on the right side when water really has to be on the left side.
How do you know that though?
Because I'm looking at the overall reaction at the top there. The overall reaction at the top says water's on the left side, right? But this step reaction says that water's on the right side. So what I'm going to do to start out with is I'm going to rewrite the the second reaction flipped. And the only thing that really changes there is that the delta H no longer is negative, it's positive. One thing that I do, guys, to make sure that I don't make any silly mistakes is I actually write the positive sign in on my delta H's so that I know that I mean it to be positive and not negative, and I didn't just forget it as I was rewriting. I do it as kind of a way to keep track of whether I did it or not. Okay? So if I were to do this reaction like this, notice after I've rewritten it, okay, so Aubrey's right on target here. The next thing that I'm looking at here is that H2 and H2 are going to wind up canceling, except there's not enough of the H2 in the first reaction, right? Okay, so I want to multiply the whole thing. Another thing that might tell me to multiply the whole thing, and this is why this is a puzzle, there's not one right way to think about it, is that how many hydrofluorics are being made in the step? In the overall reaction, it's 4, but in the step, it's only 2. Is that going to be enough? No. So I'm going to want to multiply this first reaction by 2 all the way across. And that means my delta H has to be multiplied by 2. So what am I going to get here? I'm going to get negative 1,800. No, I'm sorry. Negative 1,000. It's not 800. 1,084.4 kilojoules. Okay. So when I look at this, now the H2 and the H2, since there's 2 of each, those will cancel. I'm going to wind up with 2 fluorines, 2 waters. On the right side, I wound up with 4 hydrofluorics and 1 oxygen. So I'm going to want to go ahead and add negative 1,084.4 to positive 571.6. And I'm going to have to rely on you guys because I don't have this one pre-calculated. So when I take my negative 1,084.4 and I add it to the positive 571, I am getting 512.8 kilojoules as my delta H. Okay, it's a little bit of a puzzle. All right, I'm done. So if we're doing this problem, one of the things that I'm noticing is that this last reaction, CS2, is showing up on the product side, on the reactant side when it should be a product. So I'm going to have to flip this one around. So I'm going to rewrite this one. To look like this. And the delta H winds up getting flipped as I do that to be a positive 1,072 kilojoules. All right.
Wait, what is the? No, that's not what I.
Okay, so that's one of the changes that needs to be made. The other change that needs to be made is that the sulfurs in the second equation, there's not enough of them, right? There should be 2 sulfurs, twice as much sulfur. So I'm going to multiply the whole gosh darn thing in the second equation by 2. So that means I don't get 296.1. I get 296.1 times 2, which is a negative 592.2 kilojoules. Right. Okay. Now when I examine this, I'm seeing my 2 SO2s are on opposite sides. My 3 O2s are getting canceled because there's two O2s here and one O2 there. And my CO2 is getting canceled here and there. So ultimately, I'm getting the reaction that they're asking for. I'm getting one carbon and two sulfurs on the left side and one CS2 on the right side. So that means now I need to just add negative 393.5 to negative 592.2, and then add that to the positive 1,072 kilojoules. And okay, so that's going to be positive 86.3 kilojoules.